Hello all, welcome to our channel. In this video, we are going to discuss about counting-based optimal page buffering algorithms. This video is presented by G. Shivarama Hasani, K. Vamsi Madhavi, to Dr. M. Prasad, Associate Professor to the Department of CSC, Sri Vishnu Engineering College for Women. Let's get into the video. Coming to counting-based page replacement algorithm. What do you mean by page replacement? Page replacement is a technique of replacing a data block of main memory with the data block of secondary memory when all the frames of main memory are occupied and CPU demands for the data block that is not available inside main memory. Counting-based page replacement algorithm replaces the page based on count, that is, number of times the page is accessed in the past. If more than one page has the same count, then the page that occupied the frame first would be replaced. Coming to two types of counting-based algorithms. First one is most frequently used algorithm. It replaces the page with a count greater than other pages, that is, which is accessed a maximum number of times in the past. Least frequently used algorithm. It replaces the page with a count lesser than other pages, that is, which is accessed a minimum number of times in the past.
Now, let us consider a main memory with number of frames equal to 4 and the following are the data block access requests made by the CPU. Here we can see that the CPU requests are as follows and also given that the number of frames equal to 4. Initially, all the frames are empty. By using least frequently used algorithm, here the 4 frames are initially empty and next the first 4 blocks occupy them. That means the block 7 is occupied by the first frame, block 0 is occupied in second frame, block 1 is occupied in third frame and block 2 is occupied in the fourth frame. Step 2. Block 0 has already occupied the frame, that is, the upcoming element 0 has already occupied in the frame, hence it is not considered. Now we can see the upcoming block element is 3. But the question is where we should place this block number 3. Here we use the least frequently used algorithm to replace the block 3. Here we can see that blocks 2, 1 and 7 are accessed least, that is only once, and block 7 occupied the frame first. So block 7 replaced with incoming block 3. And step 4 is blocks 3 and 0 have already occupied the frame, hence they are not considered again. Now, in step 5, we can see that the upcoming element is 4, but again we have the same problem. Hence, here also we use the least frequently used algorithm and do the page replacement. Now, the blocks 2, 1 and 3 are accessed least here. Hence, and also block 1 occupied the frame first. So, block 1 replaced with the incoming block 4. And in step 6, we can see that blocks 2 and 3 have occupied already, hence we won't consider these changes. Now we can see in step 7, the next element, that is the upcoming element is 7. To replace this, the block 4 is accessed minimum number of times, hence block 4 is replaced with the block 7 here. And the step 8 is the blocks 3 and 2 have already occupied the frame for the next elements, hence we will not consider the changes. In step 9, we can see that the upcoming block is block 1. Here we can see that block 7 is accessed minimum number of times, hence block 7 is replaced with block 1 here. And totally the number of page faults is calculated as number of blocks not already present and bought inside the main memory. Hence we can see that there are 8 page faults from the above example.
Now, let us take another example, page replacement using the most frequently used algorithm. Example, Consider a main memory with a number of frames equals to 4, and the following are the data block access requests made by the CPU. Given the number of frames equals to 4, initially all are empty. Step 1. The 4 frames are initially empty. The first 4 blocks occupy them. Coming to step 2, block 0 has already occupied the frame. Step 3. Block 0 is accessed maximum number of times, so it is replaced with incoming block 3. Step 4. Blocks 2, 1, 3, 7 are accessed once, and block 7 occupied the frame first, so block 7 is replaced with the incoming block 0. Coming to step 5, block 0 is accessed maximum number of times, so it is replaced with incoming block 4. Step 6, blocks 2, 3 have already occupied the frame. Step 7, block 2 and block 3 are accessed maximum number of times, and block 2 occupied the frame first, so block 2 is replaced with incoming block 0. Coming to step 8, block 3 has already occupied the frame. Coming to step 9, block 0 is accessed maximum number of times, so it is replaced with incoming block 2. Step 10, block 1 has already occupied the frame. Now, let us see the comparison between most frequently used and least frequently used counting-based algorithms. Coming to most frequently used algorithm, it replaces the page which is accessed maximum number of times. Coming to least frequently used algorithm, it replaces the page which is accessed minimum number of times. In the most frequently used algorithm, since most frequently used page is replaced, this increases the number of page faults, as in future the page has higher chances to be accessed again. In the least frequently used algorithm, since least frequently used page is replaced, this decreases the number of page faults, as in future the page has lower chances to be accessed again. Now, let us discuss about optimal page replacement algorithm. The optimal replacement algorithm, also known as the OPT or Bill-Eddy's algorithm, which is a theoretical memory page replacement algorithm used in computer science to analyze and measure the performance of other page replacement algorithms. It is not a practical algorithm for real-world use because it requires knowledge of future memory access patterns, which is typically not available in real operating systems. The main idea behind the optimal page replacement algorithm is to replace a page that will not be needed for the longest period of time in the future. It predicts which page will be accessed furthest ahead and replaces it when a page fault occurs. Thus, the operating system needs information on future memory references to implement it. However, it is not practical in real world scenarios.
Here we can see the flowchart which tells about the steps of optimal page replacement algorithm. Firstly, we start, that means the frames are empty. When the new request is given, then it will be stored in the main memory. And if the page is found, then it goes to page hit and then later replace the pages with the new page. If not, if that means if the page is not found, then it goes to page miss, where we have if the memory is full, then it find a page that is accessed further in the future and replaces this page with new page. If not, it insert page into an empty slot. This is all about the flowchart. Now let us consider an example for optimal page replacement algorithm. Here we can see the page references are as given and there are only 3 slots in the main memory. So initially the memory is empty and the optimal page replacement algorithm inserts page 7 in the memory. It is a page miss, hence we have written M in the place of 7. Next, the algorithm inserts 0 in the main memory as neither its full nor 0 is present. This is also a page miss. Next, the algorithm inserts 0 in the memory as neither it's full nor 0 is present. This is also a page miss. Again, it is represented as m at the place of 0. Similarly, it adds 1 because it is not in the memory. Now, the memory is full and does not contain page 2, again causing a page miss. The algorithm replaces page 7 with page 2 since page 7 will not be used in the future. Now here we can see that the page 0 is already in memory, resulting in the page hit with no need for the page replacement. Hence there is a H represented at the place of 0. With the main memory full and the page 3 missing, another page miss occurs. The algorithm swaps page 1 with page 3 as it is not used in the future. Next, the algorithm finds the page 0 is already loaded in the main memory, hence again it is a page hit. The main memory does not contain page 4, causing a page miss again. In this case, page 0 is accessed further ahead in the page references, so it replaces page 0 with page 4. Subsequently, the page 2 is available in the memory, therefore it is again a page hit. Likewise, it finds the page 3 again in the main memory, again leading to a page hit. Hence, there are several page hits and page misses in the page replacement. Here, in this example, we can see that the total number of page hits are 4 and the total number of page misses are 6 respectively.
Coming to the advantages and disadvantages of optimal page replacement algorithm. The advantages are the optimal page replacement algorithm selects replacement pages based on future memory references, ensuring optimal memory utilization. It can efficiently detect and correct single bit errors in data without the need for retransmission. The optimal page replacement algorithm sets an upper bound to evaluate the efficiency of other page replacement algorithms. The disadvantages are the optimal page replacement algorithm relies on perfect knowledge of future page references, which is unrealistic. It has a high computational cost as it analyzes all the future page references. It lacks adaptability to changing patterns of page references.
Thank you for watching this video. If you like this video, please do like, share and subscribe to our YouTube channel.